All right, picking up where we left off yesterday, if we look at these functions, and you don't have to write this table down, but if you look at our functions, we have the function y equals x squared, and that is increasing or going up and to the right. If you think about that function and what we know it to look like, it's the parabola or the U shape, and that's going up and to the right from 0 to infinity if it's just x squared. So that is increasing from 0 to infinity, looking at our x values, and it's decreasing or coming back down between negative infinity and 0. X cubed, that one starts down low and increases from negative infinity to 0. But then if we look at the other side of it, that also just continues to go up. So that's going to increase all the time from negative infinity to positive infinity. And it never goes down. Same thing with 1 over x. If I look at that one, and for a lot of these, you're going to be able to look at the graph and see it. That's why I don't make you write the table down. Because if you're concerned about where it's increasing and decreasing, just graph it and you'll be able to see. 1 over x comes down like this and never comes back up. So the entire time, if we're looking from left to right, it's going down. So that's never increasing. And it is always decreasing except when we're at 0. And that's simply because we can't divide by 0. Uh, 1 over x squared, if we look at that one, that one is increasing from negative infinity to 0 because it looks just like 1 over x, except that on the left-hand side it's going up, because we would never have a negative number come out. So from negative infinity to 0, it's going up or increasing from left to right. From 0 to infinity, it's going down or decreasing from left to right. Square root of x looks like this. There's nothing from any negative infinity to 0. Because remember, you can't take the square root of a negative. But from 0 to infinity, it's going to be going up slightly, and so it's going to be from 0 to infinity, it's going to be increasing. And it never goes down. Last one is x to the 2/3. And when we look at that one, that's going to be decreasing from negative infinity to 0 and increasing from 0 to infinity. I think that one looks like this and this. So from negative infinity to 0, it's going down as we go from left to right, and then from 0 onward, it's going up. So that's a basic rundown of those graphs. If you just look back at the graphs that we've done over the past few days, you would see every one of these. Like I think we had, yeah, so that's why I didn't make you write the table down, just because we have all of those graphs written down already. So if you wanted to know where it was increasing and decreasing, you could just look at those. All right, that takes us to even and odd functions. Even and odd functions have certain characteristics of symmetry. A function y equals f of x is an even function of x if f of negative x equals f of x, and it's an odd function if f of negative x equals negative f of x. Then the graph of an even function is symmetric about the y-axis, and the graph of an odd function is symmetric about the origin. And we'll look at exactly what this means here in a second. So for an example, we're going to look at this to see if it's even or odd or neither, because that's always a possibility. And then we'll look at the graph to see what that means about symmetric about the y-axis and symmetric about the origin. So in order to tell whether this is a even function, so for an even function, from our last page we had f of negative x has to be equal to f of x, right? So what that means is if I plug a negative x in here, it should give me the same exact equation. So when I plug this in, f of x is just our equation, x squared plus 1. F of negative x, plugging a negative x in, everywhere we have an x. Now if I solve this, a negative x squared is the same as an x squared. And so this is equal to our original equation. So this would be an even function, because these two are the same. If I look at the graph of this, that's the worst y-axis that's ever been drawn. If I look at the graph of this, it starts at 1, and from there it goes up 1 and over 1 in both directions. And so this is symmetric about the y-axis, meaning that if my y-axis is my axis of symmetry, if I flip this piece over, it would be exactly the same as this piece. So if I flip this side across the y-axis, like I was folding a sheet of paper, it would perfectly overlap this side. So that's how you can tell graphically if it's an even function. Algebraically, you can tell by plugging a negative x in everywhere you see an x. Since it's even, we know it can't be odd, so we're done. But if we had checked to see if it was even and it wasn't, then we would need to check and see if it's odd. You good with that one? Let's check another example. Here we have f of x equals x plus 1. So I start by plugging f of negative x in. So that becomes negative x plus 1. Then would that be an even function? No, because it's not the same as the original. So now we need to check to see if it's an odd function. For an odd function, this f of negative x has to be equal to negative f of x, which would be the same as multiplying the entire thing by negative 1. So if I multiply all of this by negative 1, I have to distribute this negative. That would become negative x minus 1. Now, are these two the same? Those are not the same because I have a plus 1 and a minus 1. That's perfectly fine. The whole point is that if we look at this, and then if I look at it graphically, because our original was x plus 1. When it says it's got to be symmetric about the origin, what that means is if I took this piece and folded it around 0, I would have a line that comes down like this, right? Which would not match up with where this line is. So whenever they talk about being symmetric about the origin, an example of an odd function would be like x to the third. And the reason that that one is odd is because if I took this piece and I just swung it around the line or the origin, or I just took this top half of it and swung it around, it wouldn't match up perfectly with the bottom half, which makes it symmetric about the origin. Here, if I took this top piece and swung it around on here, it's not going to match up down at 0, 0. So graphically, you can see that that's not symmetric about the origin. If we looked at that x to the third, or x cubed, algebraically, if my original is f of x equals x to the third, then I first have to check it by doing f of negative x so I plug a negative x in for x. Negative x to the third is still a negative x to the third. If I did negative f of x, that's going to be just putting the negative in front of x to the third. And you can see that these two will match up. So that makes that an odd function. This one, I guess I did not finalize that. Thank you. That one is neither, because it didn't match up. F of negative x is not equal to f of x, and f of negative x is not equal to negative f of x. So that one ends up being neither. So good with that one? Mm-hmm. Alright, this last piece is about proportionality. And its two variables, y and x, are proportional to one another if one is always a constant multiple of the other. That is, if it's some non-zero constant k. So y would be proportional to x if your equation was of the form y equals kx, where k is just some number, like y equals 2x. Or y equals even 2/3 x. And those would be proportional to each other. If I threw something else in there, like say y equals 2x plus 1, this is no longer proportional. That plus 1 throws it off. So if we're talking about proportionality, you just have to make sure that you're paying attention to the fact that there's nothing behind the x, nothing being added or subtracted from it, and we're just multiplying some number that's not 0 times the x.